will lead us to a major conjecture of Serge-Lang, and we'll discuss that. In fact, the way it's written, it seems like 1 hour per lecture, but that's not true. In fact, I would wish to spend all of the time on lecture 2, but it's not going to be possible. So I think lecture 2 will not start on Wednesday. It will start before, okay? At least that's my aim. The minimal model program is what Brendan learned when he participated in that seminar 13 years ago. It's a beautiful theory, and I'll only teach you about the beautiful stuff, because there's also ugly stuff there, and I'll completely ignore it. Okay? And that's one topic that I think number theorists should know more about. And I think Yuri must have alluded to some of the things that come up there. The last lecture, maybe I will get to it, maybe I won't. It tries to tie together some of the notions that will occur earlier. All right, so let me start. Start by following what, so I should say, well, so here's a statement. Geometry determines arithmetic. Already in the first lecture of Chinkel, we heard, I guess I wasn't there, but it's a collective world, we heard that this is complete nonsense, because there's a theorem that says that arithmetic is complicated, more complicated than anything you can imagine, right? There's a theorem that Diophantine equations cannot be solved in general. But that does not stop us from working in arithmetic geometry, does it? So what we try to do is throw away some of the randomness and some of the ambiguities and concentrate on things that are determined by geometry. So the word geometry, I'll concentrate on the birational geometry of a variety X over a number field K. There's other geometries you can study, and which will occur in other lectures probably, but I don't know enough about them to say anything. Arithmetic is what we've heard about all along, rational and integral point, at least after a field extension. So one major point where I try to get rid of the randomness is by allowing myself to extend the base field, which is somewhat in contrast to what Darmon has been doing in his lectures. And what does determine mean? Well, that's to be determined. All right, so the first topic is what Darmon's lectures were about last week, is about closed curves, namely smooth projective algebraic curves over number fields usually. And to summarize what Darmon has been telling us, I guess I wasn't there, but your lectures are not on the web yet. Okay, so to summarize, there's an invariant that tells us what we should expect the arithmetic of a curve to behave like. And the invariant is the genus, or the way I want to think about it from here on is 2g minus 2, which is the degree of the divisor of a differential, of a canonical differential. So if I look at algebraic curves whose 2g minus 2 is non-positive, so this means curves of genus 0 and curves of genus 1. If I take such a curve over a number field, well, it might have no points at all, but I know that that's an accident, that if I extend the field, as I suggest here, if I extend the field, I remove some of this ambiguity that is so interesting and so important for people like Darmon. But if I want to say something about this nonsense, geometry determines arithmetic, I have to do this trick of getting rid of some of the ambiguities. So this is what I call potentially dense. Well, I'll say that in a minute. And if the 2g minus 2, if the genus is positive, bigger than 1, sorry, namely 2g minus 2 is positive, then we have finite. So in other words, rational points on a curve C of genus G are potentially dense if and only if the genus is less than or equal to 1, where potentially dense means dense is the Zariski topology, which for a curve just means infinite, right? For an algebraic curve, dense means, in Zariski topology, means infinite. And other topologies, are important. I will not refer to lectures from last week. Are potentially dense if and only if the genus is less than or equal to 1. So potentially dense, I said what potentially dense is, and I need to say what Kc is. So Kc is a divisor class. That's the usual terminology used in birational geometry, although geometers have this bad habit of confusing divisor class and line bundles. So I'll try to avoid this, but I am a geometer, so I will do it. I can guarantee almost. So OC of Kc, so Kc is a divisor class. I take the associated invertible sheaf, which I really confuse with line bundles, okay? I never distinguish between them. So that sheaf is the sheaf of 1 differentials on C of holomorphic differentials if you are a geometer, or algebraic differentials if you are an algebraic geometer, which for curves is the same as the dualizing sheaf that occurs in third duality, omega C. Let me just say a word about this. We know that the case where a genus is less than or equal to 1, this table says, or this displayed statement says that the rational points are potentially dense. Well, you just do it. How do you show this? You just do it by hand. Okay, so what do I mean by do it by hand? If you are on a rational curve, well, on a curve of genus 0, then you know that it becomes rational over an extension of a degree at most 2. And once it's rational, you just write your points. They're there. For a curve of genus 1, that's a little bit more of a problem. So the first thing, the major problem is to find 1 point. And for that, you might need to take an arbitrary degree of an extension. But once you have 1 point, you have an elliptic curve by Darmon's terminology. Now, you might have still only finitely many points on an elliptic curve. But after a further quadratic extension, there will be infinitely many. So that's over a number field. There will be infinitely many. So that's easy. The case of genus bigger than 1, that's a major theorem that took 1 lecture of Darmon's lecture series, which is the theorem of Faltings, which has enjoyed many further proofs later on, at least 1 major proof by Faltings, that if C is an algebraic curve of genus bigger than 1 over a number field K, then the set of rational points on that curve is finite. Now, you also had a lecture by Chinkel about integral points. Which touched on things that Darmon also covered, but I don't have Darmon's lectures on the web, so I'm just guessing that it, of course, you can talk about projective algebraic curves, but you can also talk about affine algebraic curves. And if you think about it, rational points on an affine algebraic curve are almost like rational points on its completion. When you add a few points and you get the completion. So rational points are not a further interest. But there is something, for instance, on the affine line, so just coordinate x, you can be interested in the integer coordinates. And integral points are indeed interesting on the affine line, but you have to be careful. Because if you take the affine line, well, the affine line is defined over the rational numbers, right? So you can cook up an automorphism of the affine line which sends x to 1/2 x, right? This is an automorphism defined over Q. This is an automorphism of the affine line over Q, which in particular sends the point x equals 1 to the point x equals 1/2. And this is not an element in any definition that you would want to have. This is not an integral point, right? It's not an integer coordinate. So what this says is that just working over your field is not enough. And that was a major point that Chinkel made in his lecture. In order to make sense of integral points, you have to work with a model of your variety, in this case a curve, over the ring of integers, or something like the ring of integers. Otherwise, it is not an invariant notion. In other words, for open varieties, we use integral points on integral models, on schemes defined over some base scheme, which is the spectrum of the ring of integers. We'll get to this in a moment. What I want to point out, if C is an affine curve with completion C, I'll use the terminology sigma for whatever is left over. C bar minus C equals. This is the set of points that we throw out. Probably Chinkel used another terminology, but I forgot to check it out. And I want to have something that is analogous to the canonical sheaf to the sheaf of differentials on a projective curve, and the best analog we know of is the divisor class Kc plus the points removed taken with multiplicity 1. This is called the divisor of a logarithmic differential. So I think I should revisit this in a minute. Let me just put this up, go over here, make sure I'm on track. All right, so if you recall, you might not recall from Chinkel's lecture, you replace the number field K with a ring of integers, basically. So just working over the ring of integer itself is not going to be sufficient for me. I want to also invert a few primes. So S is a finite set of primes, if you want prime ideals. So this is the same as I would write it this way if the primes were really principal, but in general you can think about what this means. It's you can work with just OK with some element inverted. That's interesting enough. So the base scheme I will work with is a spectrum of this. And what I have, the picture I have, here's C. And I add a few points. So this is, so C bar is what I get by completing it. Here's spec K. And here's my picture a la Mumford of spec OKS. If you look at Mumford's book, he introduced this ridiculous picture of the spectrum of a number ring. Of course, it's just a bunch of points, but a prime. And so I take a scheme which spreads out. I just take the equations, if you wish, of C bar and take those equations over OKS. That gives me a scheme over OKS. And so that I will call C bar. And here's the points of sigma. So this I'll call sigma bar. So the closure of the points of sigma will give me some And the complement I'll call C. In fact, I can take any model of C, any scheme whose restriction to spec K is C, but it's usually more convenient to take just the complement of sigma bar in some completion. So now I need to define what integral points is in general, and this is, again, I recall what Schinkel did for you last week. An integral point so if I have a point here, a point P, I can think of it as a section from spec K to C. And once I have that, I can look at its closure. So that would be just a rational point. But I declare it to be an integral point if it's a schematic point of this model C. So if it is really a section of the open part C so it really lands in the scheme C, not C bar, in which I'm interested. So these are exactly, to recall what Schinkel said, these are exactly the rational points such that at every prime, the reduction of this point to this prime does not meet the points of sigma. So here's a non-integral point. This is not allowed. Okay. I just want to point out that if you take a proper curve, then the fact that when you take the closure of P, you get something that is a section, means that for proper curves, I haven't changed the notion. So for instance, for P1, integral points are the same as rational points. That's another thing that Schinkel told you last week. On a proper curve, if you don't throw away things, this is nothing new. Okay, so that's this discussion. And here's the analog of what we had for complete curves for when we search for an analog for open curves. We have a table that says that the invariant that I claimed is the right analog actually is the right analog. So if I take the degree of the sheaf of logarithmic differentials and compare with integral points, then indeed, if 2g minus 2 plus n is less than or equal to 0, the integral points are potentially dense. And if 2g minus 2 plus n, so that if the degree is bigger than 0, then the points are finite. Again, let me just, before I explain why this is true, potentially dense, I need to explain that, and that's because there's one example that I will tell you about in a minute is that of the multiplicative group, which is an affine curve defined by the equation x times y equals 1. And you know that over Q, there are only finitely many solutions, namely plus or minus 1 for x and plus or minus 1 for y. But over a number field, I guess, not every number, if n1 plus n2 is bigger than 1, so if so over a number field which is not just a quadratic imaginary field, there are solutions. There are infinitely many solutions. So these are the unit. Okay. But if I look at a similar equation which is isomorphic to this over Q, then whatever ring of integers I will take, I will have no solutions. Right? So the point is that extending the number field is not enough. I need to also throw in the S's. I need to invert. So need 1/2. So without doing that, then this statement is not true. So that's at least one reason why to introduce S integral points into the picture. This is not really the reason, but but certainly you see that it's necessary there. So since I've written this example, I already can tell you why. So we have already almost dealt with all the cases here. The exception, the one case, the two cases we have not looked at is P1 minus 1 point, which I'll call 0, and P1 minus 2 points, which I'll call 0, well, maybe I'll call this infinity, 0 and infinity. Of course, not every curve of genus 0 with degree 2 divisor removed is one of these, but it becomes one of these after an extension, so that's why I need to extend the field. And then, in this case, in the affine line, you can write infinitely many integral points. We know them, the integers. And on the affine line minus 2 points, you need to go to a number field to get units. And if you indeed have something like this, then you might need to invert some primes. So I've already done it on the board, so I don't need to write anything here. The case where there's a finite net statement, again, is the case where there's a true arithmetic content there. We already mentioned Faltings's theorem in the case of genus bigger than 1. There are still a couple of cases, namely an elliptic curve with a point removed, at least 1 point removed, or rational curve with at least 3 points removed. These both fall under the older theorem than Faltings, which says that if you have any affine curve, so either n bigger or equal to 3 or the genus bigger than 0 and n bigger than 0, then for any of these affine curves, any of the affine curves, affine cases that fall in the second line, then for any integral model of your curve, the set of integral points is finite. So that's something that predates Faltings, and the techniques that go in there definitely are used in proving Faltings's theorem, Ziegel's lemma. But one of the really one of the holy grails of this subject is people want to have a way of deducing Faltings's theorem directly from a Ziegel-type result. That would be really wonderful, and one expects that it would give us better results on Faltings, but what? I know I'm repeating things that you have done. So, but what I want to point out now is that, in fact, the outer direction has been known for a while. And it has already occurred in the lectures. I mean, the techniques occurred in the lectures of Darmon, and the only reason I know that is that he alluded to it today. And I guess it occurred in the exercises, this actual thing. So the main point is that Darmon introduced last week for this purpose is the fact that rational, and he mentioned it today too, that rational integral point can be controlled in finite étale cover and finite unramified covers. I guess for number theories, I should not use étale, but I should use unramified, which is the same thing, but it has an older history in the number theory world. Namely, you have a finite unramified cover of algebraic curves, then at least away from some discriminant, if you invert some discriminant, then you can say any rational point downstairs becomes not necessarily a rational point. If you pull it up, it's not a rational point, but there's a particular field, one algebraic number field, over which it becomes rational. So here's I'll just review what's behind what Darmon probably taught you last week. There's a theorem of Hermite-Minkowski, which says that if K is any number field, as S is a finite set of finite places, of primes, and of non-zero prime ideals, let's say, and d is a positive integer, there are only finitely many extensions of the grid, most d, unramified outside S. That's a classic theorem of Hermite-Minkowski. In particular, it's used in understanding that if you fix the degree and discriminant of a number field, that's a good measure of how big the number field is. There are only finitely many within this ball. Okay, you can, for each degree and size of degree and discriminant, you make a sack of all the number fields, and it's not so heavy because it's finite. But for our purposes, you can deduce from this is that if you have a finite étale morphism of schemes over the ring of S integers, OKS. And since I'm a geometer, I'll actually attempt to draw something like this. So these ramified points are removed. And so I want the morphism to be étale, unramified, and I want it to be finite, so that I can pull up points from downstairs. Then there is a finite extension. There's a fixed finite extension, which is exactly what you have here, such that if you take the set S prime lying over S, and then any integral points on Y, so this is Y and this is X, any integral point of Y pulls up anything in the inverse image is an integral point on X, not over the same field and not the same S, but over the bigger field. Okay, so it's good to know that this was an exercise last time, because I can now, okay, so on the geometric side, we have an all topological result. So what do we want to do? We want to take a curve, a Siegel curve, a curve with 2g minus 2 plus n positive, curve which we want to show has only finitely many integral points. We want to produce an étale cover by another curve. So we know that integral points downstairs are bounded by integral points over some field upstairs. But in order to use Faltings, we want to have the curve upstairs have big genus. And that's what the geometric result tells us. If C is an open curve with 2g minus 2 plus n bigger than 0, and let's take, I don't actually need n bigger than 0 for this. I don't know why I wrote that. Defined over number field. There is a finite extension of number fields, and a finite. So here's my curve C. So there might be some sigma here, but in fact I don't need it. There's a finite extension, a finite unramified covering, so which means that it's a finite covering of the complete curves, which is unramified away from the points of sigma, such that the genus upstairs, this is the curve D, such that the genus upstairs is bigger than 1. Okay, and once you have this, you can use the theorem of Chevalier-Vey to say, well, okay, I'll take an integral point downstairs. Well, I have to take an integral model. So what I need to do is I need to extend both C and D to an integral model. And if I do it right, then at least after inverting some primes, I'll have an unramified cover of the integral model. So the integral model of D will be unramified over the integral model of C. That's only true after throwing away some primes, but that's okay. And therefore, every integral point downstairs will become an integral point upstairs, in particular a rational point upstairs, and by Faltings, there are only finitely many. So how do you do this? Well, that was an exercise last time, but you can just do it by hand, right? For instance, if you take P1 with 3 points removed, you can take your usual cover. You can start with your usual cover of P1 by taking an n-fold cover that is branch over 0 and infinity by just taking an nth root of t. And then you can take another cover that is branch over 0 or maybe 1 and infinity, which is obtained by taking an nth root of t minus 1, I guess. And then take the join of those. And if you do such things, you'll get curves of genes bigger than 1. And that's fun to do. So since it was an exercise, you might as well pursue it if you haven't yet. There's the case of an elliptic curve with 1 point removed is also an interesting case. So in that case, you need to do a little more. You first need to cover the elliptic curve by one of its usual étale covers by the isogeny, and then you have many points on the elliptic curve. And if you're careful, all right. So that was an exercise. I'll leave it as that. I'll leave it as that. All right. How am I doing? All right. This way. I'm jet lagged, therefore I had too many coffees today, which means I'm going too fast and you'll have to stop me. I'm not going to stop myself. Okay? So if you have questions, you should not let me just rush ahead. Right. We have learned, did we learn last week that anything over number fields, not anything, but many things over number fields have good analogs over function fields, and the study of this analogy has been a very, very fruitful way of understanding what to expect to be true over number fields, and in general, I think a big contribution of Grothendieck's development of the theory of schemes is from this analogy. So if K is the function field of a complex variety B, then a variety of X over K can be thought of as the generic fiber of a scheme script X over B. So here's B. Here's the generic points by K. And here your variety X. And you can kind of sort of spread it out. There might be some very, very singular fibers, of course. But you can try to spread it out to some scheme over B. A K-rational point can be thought of as, so if you have a K-rational point, you can take its closure. So its closure will be something that looks like this. It might have some, it's almost like a section of script X over B, but it might have some poles. So it's really a rational section of X to B. You just take the closure. That's a scheme of degree 1 over B, namely it's birational to B. So it's almost a tautology to say that it's a rational section of this. In case the dimension of B is 1, and in case X over B is proper, then just as we had in a previous transparency, I mean, you take the closure of something, you get something of degree 1 over B, the closure will not have any fibril components. So the evaluative criterion for properness means that you actually have a regular section B of X in the case of dimension B equals 1. So really you have a relationship between rational point on X and section of script X. So that's a way to give a geometric meaning to rational points when you work over function fields. And so this is an analogous situation to the question of rational points over number fields. And the analog of Moldell's conjecture, namely the theorem of Faltings, was proven many, many years before Faltings proved the Moldell conjecture over number fields. In this situation, assume that the genus of C is bigger than 1, then the set of rational points are finite with one caveat. So here's a picture. Now, here's a point curve C naught, and you can always, if you have a variety B, you can always form C naught cross B, which maps to B. And if C naught has infinitely many points, look, I've said B is a complex variety, so any curve over the complex numbers has infinitely many complex points. Then there will be many, many, many points like this, namely the constant points. So what Manin and Grout actually prove is that assuming that genus is bigger than 1, there are only finitely many non-constant points. So they prove exactly what you expect to be true. But they are rational over the complex numbers. So I'm thinking about, so the function field of B is a function field over the complex numbers. So sections are going to be just sections over the complex numbers. So this is not arithmetic, really. It's geometry. So I'll get back to your question, to your point in a minute. What happens when this is not over a complex number, but over? Okay. Right. Yeah. So the theorem is particularly geometric in this particular case because what it says. So what's a rational point here? A rational point is a section from B to B cross C naught. But what's a section? The data of a section. Well, we know how a point of B will have to map to itself on a point. So a section is just a graph of a map from B naught to C. And the theorem of differentiation says that there are only finitely many non-constant ones. And you can actually say something about how many in terms of the way the Jacobians look and so on. So that's the theorem of Manin and Grout. Now, back to your point. Instead of working over the complex number, let's pull back and say, well, function fields can still have some arithmetic content if these are function fields of varieties over Q or over a number field. Namely, these are fields that are finitely generated over Q. And if you combine the theorem of Manin and Grout and the theorem of Faltings, you can immediately prove that I think that's one of the exercises in my... I hope everybody knows that there are lecture notes available. I don't know if everybody, certainly you have access to them on the computer. And there's an incomplete set of exercises there, but I think it will keep you busy for this week. Right, so you can combine this easily, and that's an exercise, and prove that this... I still call it Faltings' theorem, and I would not be surprised if Faltings actually mentions it in one of his papers, but it doesn't matter. If C is a curve of genus bigger than 1 over a field which is finitely generated over Q, so these are slightly more general, arithmetically interesting fields, then the set of K rational points, you don't need to worry about non-constant in that case because of that point exactly. The set of K rational points is finite. Okay? Combination of Manin and Grout and the earlier stated theorem of Faltings. All right. That ends lecture 0. So questions about curves. So the reason I did this very elaborate review is, A, probably nobody complains about a review, right? And second, I need to draw some points from the curve case in order to seek for analogies in higher dimension. So remember what I said in the beginning, geometry determines arithmetic. That's true for curves. All these theorems say that's true. 2g minus 2 plus the number plus n determines the arithmetic of the curve up to, okay, so it doesn't determine completely because we want to count these points, you want to measure these points, you want to know many things, but at least in the low level sense, it does determine. Almost anything in higher dimension is conjectural. Yes? Arbitrary fibration with fiber isomorphic to. Oh yes. Let's. So this is. Here I did not. I stated here just the rational point case. So the way I stated it, I don't need a fibration. Oh, you mean this theorem? This theorem. Yeah, this is true in general. This is a theorem about function fields. I don't need to choose the model in order to state the theorem. I chose the model in order to explain. There is a point. Thank you. There is a point. So I chose the model in order to explain the geometric underpinning of what this means. But also, if you want to work with integral points, which I haven't mentioned here, it's mentioned a little bit in the lecture notes, you have to choose just a fibration. Or the number of possible fibration with the same generic fiber, that's infinite. You can always take a point here and blow it up. So you'll have to, there is a whole theory, well, okay. I'll get to talk about minimal models later, but but I think you are four steps ahead of me. Okay, now we start with lecture 1 about Kodaira dimension. So the first thing that I want to do, and that's what Kodaira dimension is about, is find something analogous to the degree of the canonical sheaf of a curve. So for the time being, K will just be a field of characteristics 0, not necessarily a number field. There are troubles in positive characteristic. Some of them are due to inseparable maps. Some of them are due to issues of Hironaka's theorem not being available. So I'll stick with characteristic 0. Suppose X is a smooth projective variety of dimension D, and L is a line bundle on X. So I'll define something for general L in a minute. A specifically interesting line bundle is the line bundle whose divisor class is called the canonical divisor class Kx. So the line bundle with divisor class Kx is the sheaf of top degree differentials on. So you take the one forms on X and take the dth exterior power, that's D is the dimension of X, which is again the same thing as the dualizing sheaf of X. So in higher dimension you don't take omega 1X, which is an interesting sheaf nevertheless, but you take its dth exterior power, which is a line bundle. Since omega 1 is a vector bundle of rank D, it's the cotangent bundle of X. Then it's this exterior power is a line bundle, and that's what I want. I want a line bundle. And the reason why this is particularly interesting is that I'm teaching you here about birational geometry. Sections of this line bundle are a birational invariant, and in fact, sections of OX of any positive multiple of are birational invariant for any m. I guess m bigger or equal to 0. And the reason for that is explained in Hartshorne's book. It's a very beautiful result. If you have two varieties with a birational isomorphism between them, well, there is an open set in U such that this is a morphism, right? And this is an open set whose complement has dimension at least, a codimension at least 2. You can always extend a rational map away from codimension, across codimension 1, namely up to codimension 2 things. If I have a differential here, f of z dz1 dzn or whatever, I can pull it back by the usual differential forms pull back. That's one point where I need, oh, well, here I don't need characteristics. This works in general. I can pull it back. That gives you a differential on U, which is a section on a line bundle, of a line bundle, which is well defined away from codimension 2. But U is inside X, and X is non-singular. So any section of a line bundle, locally it's just a rational function. Any rational function which is regular away from codimension 2 is actually a regular function. It can extend across codimension 2. Therefore, you get, for any section here, you get a unique section here. So you get an injection from sections here to sections here, and of course, this is symmetric you get. So I guess it must be in the exercises that I wrote, but I gave you the main. This is in Hartshorne. So this is a particularly interesting line bundle. In particular, well, it's definitely an analog of what we did for curves, and moreover, it's a birational invariant. Its sections are a birational invariant. Here's a fundamental theorem. It's in Itaka's book, and it was pointed out that the construction was earlier made by Moishazon before Itaka introduced it, in a particular case. So the theorem says that if you have an algebraic variety X and you have a line bundle, then sections of powers of that line bundle, I hope you can read up there. So little h dot is the dimension of the space of sections. Then the dimension of the space of sections grows polynomially. So I want to write, what I want to write is that h naught of x L to the n is like n to some power, kappa, times some coefficient, plus lower order term. Unfortunately, that's not entirely true, but it's almost true. So gross polynomial means that the leading term in this is well defined, even though it doesn't quite look like this. So you divide by n to some kappa, and you take the lim sup of the fraction. Then that lim sup is well defined for, so there's a particular kappa, integer kappa, for which this is a well defined and non-zero number. And that's assuming, well, that's assuming yes, so note that there's an assumption here. If there is some section, then it grows polynomially. This kappa is called the Itaka dimension of X with the line bundle L, of the pair X comma L. And in particular, if you don't write L, you mean the canonical sheaf, Kx. So That's called the Kodaira dimension of X. Yes? In characteristic 0, but not in characteristic P. Yeah, so in characteristic 0, the only abstraction for this being really a polynomial is periodicity. If you take a line band, a torsion line band on an elliptic curve, let's say, or any curve, then it won't have sections unless you take multiples of n, where n is the order of the torsion. And that's basically all that messes up polynomiality in characteristic 0. There's a paper of Katkowski which shows what happens in characteristic P. I didn't bring the precise citation, but you can find it. So this is the Kodaira dimension. I made this assumption that there is a section somewhere, and just to be complete, we need to make a definition of the Kodaira dimension. Otherwise, and the commonly used definition is that if there is no section anywhere for positive integer n, then you call the Kodaira dimension minus infinity. And the reason you use minus infinity, if you think about it a bit, you'll think that the right number to put there is minus 1. But then if you think about it a bit more, you'll see that minus infinity is a better choice for. So that's a kind of a little annoying problem with these things. So where does this number come from? What is this kappa? So kappa is an integer. And one way integer come in algebraic geometry is as dimensions of things. Right? So kappa is a dimension of something, and that's what it is. So assume that, let's assume that we don't have this negative Kodaira dimension. Assume that the kappa xl is bigger or equal to 0, namely there is some section of L to the n for some n. Then for sufficiently high and divisible n, so avoiding distortion business, the image of the rational map from X to the space of sections of the projectivized space of section, so there's a canonical map for any line bundle which has some sections. The image of that map does not depend on n up to birational equivalence. Namely, if you replace n by 2n, the image will be birational to the image for n. And because of that, I can attach all sorts of numbers to this line bundle with X, namely the numbers that are attached to this image, birational invariants of this image. In particular, its dimension is a birational invariant. So the dimension of this image is kappa XL. And it's a slightly elaborate exercise to show this, and it's an exercise in the lecture notes. That takes some work. It's definitely explained in Itaka's book, and a little more sketchily in Vojta's book in the beginning. I think he mostly refers to Itaka's book, but you can get the gist of it. The birational equivalence class of this image, n0 is the first time that this occurs. Of this image is called IXL, I for Itaka. It's the Itaka image of XL. And this rational map from X to IXL is called the Itaka fibration of X with the line bundle L. This is always it's a rational map. Its generic fiber is connected, and it is geometrically connected, and so it serves to be called a fibration. The particular case where L is the canonical bundle, this is called the Itaka fibration just of X. You just don't need to mention L, written X going to I of X. You don't need to mention L. And here's a key definition that I will come back to many times. The variety X, I think Chinkel has already introduced this last week, or the previous week. The variety X is said to be of general type. X is called a variety of general type if this codary dimension equals the dimension. This is a very bad name, general type. It stems from the fact that in the surface case, all the other cases can be completely classified, and the general type case is kind of a zoo of wilderness. So it's not a particularly good name, but we are stuck with it. I just emphasize here that this codary dimension of X, because the space of section is birational invariant, then the image of that space of section is a birational invariant. So the codary dimension is a fundamental birational invariant, a very rough, not very precise. Like you can, for each M, you can take just the dimension of the space of sections. But the kind of a rough and still useful invariant is the codary, birational invariant is the codary dimension. I'm told it's more correct to say kodaira dimension, but I revert to bad Japanese once in a while. Some examples. Well, okay, so before I do this, let me give one example that is so if you take any variety and you take an ample bundle, then for some power of L, it will have enough sections to map X isomorphically into projective space. So the Itaka dimension in this case is just the dimension of X. So let's look at a couple of examples. What do we have with Pn? Well, what is omega of Pn? That's a formula that you have in Hartshorne, which says that that omega Pn is of minus n minus 1. Or maybe I should write minus n plus 1. So since it's negative, there are no sections. And no power of it will have sections. So there are no sections at all for positive n. So the codary dimension of Pn, oh, that's written there. Codary dimension of Pn is minus infinity. If you take an abelian variety, because it's a group, the sheaf of differential is a trivial sheaf. You can pull back by translation. So for any power of n, nkx is just a trivial sheaf, so it has just one dimension of sections. And therefore, the image by the rational map is just a point. So the codary dimension is 0 for an abelian variety. If you take a hypersurface, so D is a hypersurface of degree n, then omega D, well, this is something that is true in general. This is the adjunction formula. It's omega Pn twisted by D restricted to D. That's the adjunction formula. So this is OD of minus n plus 1. Oh, I shouldn't say n. This is not n, of degree D. Minus n plus 1 plus D. So we can read immediately out of this what is the codary dimension. If D is bigger than n plus 1, then this is ample. Therefore, the codary dimension is n minus 1, the dimension of D. If D is equal to n plus 1, like a cubic in the plane, because the canonical sheaf is trivial, therefore the codary dimension is 0. If D is less than n plus 1, you have a codary dimension minus infinity. There are no sections at all. For curves, the codary dimension is exactly determined by the genus. If G bigger than 1, it's 1. If G equals to 1, it's 0. And if G equal to 0, then it's minus infinity. Okay, let me just say this last thing. This is one of the little exercises that you have in your lecture notes. The Codard dimension of a product with a product line bundle. You have two varieties, one line bundle here, one line bundle here. You can pull back the line bundles to the product and tensor them. That's called the exterior tensor product. That's this funny thing here. Then the Codard dimension of the product with the exterior product line bundle is the sum of the Codard dimensions. That's called the easy additivity theorem. And you can easily, because it's easy, this is not as hard as the previous exercises. In particular, the Codard dimension of a product variety is the sum of the Codard dimensions. This is where minus infinity is important. This is where minus infinity is important, because if you take Pn here, the Codard dimension of Pn cross something stays minus infinity. So you check that. Yeah. So in order to prove this, you need to be careful about the case where there are no sections. Okay. I think it is a good place to stop.